Hi, welcome back. We are starting Unit 9, and this is going to be a combination of 9.1, 9.2, stratospheric ozone, and stratospheric ozone depletion. Our learning objectives for today are to explain the importance of stratospheric ozone to life on Earth, to describe the process of stratospheric ozone destruction, and to describe ways to prevent stratospheric ozone destruction. So first, I just want to make sure that we're on the same page with the differences between stratospheric ozone and tropospheric ozone. So remember, tropospheric ozone is existing in the portion of the atmosphere that we exist in. This is the type of ozone that we don't like. Tropospheric ozone generally forms as a result of nitrogen dioxide reacting with VOCs in the atmosphere to form ground level ozone. We don't like this because it tends to trap heat and is a precursor to photochemical smog. Now, stratospheric ozone, which is the one we're going to focus on today, is the one that occurs in the layer just above us in the stratosphere. And this one is naturally occurring. It has nothing to do with anything anthropogenic and is beneficial to us because it acts as a protective shield against both UVB and UVC rays. So just a reminder, we actually have three different types of ultraviolet radiation. That's UVA, UVB, and UVC. Ultraviolet radiation is what we're largely concerned with damaging biological matter to us. So things like skin cancer, damaging your eyes, etc. Now, the good news is UVC and UVB are largely blocked by the ozone. UVC is the most damaging one, and all UVC gets blocked by our naturally occurring ozone, and we really like that. UVB is the second most harmful, and most of it gets absorbed by the ozone layer. Some of it gets through, but luckily most of our sunscreens, sunglasses, things like that protect against both UVA and UVB, and you can see most UVA does actually make its way to the surface of our planet. So those are the ones we're mostly concerned with. So how does stratospheric ozone actually form? Now remember, it's naturally occurring, so it doesn't have anything to do with anthropogenic causes. Now, oxygen or diatomic oxygen is going to naturally be occurring in the stratosphere. When diatomic oxygen or elemental oxygen interacts with UVC, this is UVC specifically, that UVC will separate those two oxygen molecules from each other, and we'll have two what we call free radical oxygens. Now, oxygen is really unstable in this form. It wants to be paired with a buddy. So these two free radical oxygens will move around until they find their friend. And what they'll end up pairing to is a diatomic oxygen. They'll want to form or bond together with something that is already really stable, like diatomic oxygen. And so, of course, when this free radical oxygen combines with that, we get ozone. Now, after that, so this is good. We like this formation. However, in the stratosphere, ozone is actually constantly forming and breaking down, forming and breaking down. The reason that's occurring is because we also have these ozone molecules breaking and forming in the presence of UVB radiation. UVB radiation actually destroys ozone. And so what it does is it takes the O3 molecule and separates it back into these O2 and O, and the whole process starts again. So this will occur indefinitely as long as there is UV entering into the atmosphere. We like this because as long as the sun is shining, we should have an ozone layer above us. And we call this constantly occurring, breaking down and forming, a steady state equilibrium. Now, what are we mostly concerned about here? You've probably heard the term that there's a hole in the ozone. That's something that I know I've been hearing a majority of my life. So what's causing holes in the ozone to form? Now, holes in the ozone are formed from anthropogenic causes, and the main cause of them is something called CFCs, or chlorofluorocarbons. You don't need to know the full term, just CFCs is fine. These are going to be something that is human-made. It's a human-made compound that contains chlorine, fluorine, and chlorine, just like the name suggests, and sometimes hydrogens if we're talking about hydrochlorofluorocarbons, but usually just CFCs. These were originally introduced in the 1930s when we started adding coolants to refrigerators to keep our food cold. We also use them in aerosol sprays, propellants, solvents for foam blowing agents, some insulation for electricity. We used them really frequently because they're non-toxic, they're non-flammable, they can easily be converted from a liquid to a gas or vice versa, and they worked really well for what we needed to use them for. The problem is they are readily released into the atmosphere. So if you've ever used an aerosol spray like a hairspray or a shaving cream or anything like that, probably not today, we don't use CFCs, but prior to like 1994, then it probably contained a CFC, and once you spray it, those CFCs just get released into the atmosphere as a gas. So why is that a problem? Well, the chlorine portion of CFCs is actually the problem. So when CFCs get released into the atmosphere, the chlorine gets separated from the rest of the molecule and becomes a single independent chlorine. It gets separated by UV light. So now we have this free radical chlorine. And again, free radical chlorine actually doesn't want to be alone. It either wants to be bonded to something, and in nature it generally is bonded to another chlorine atom. It likes to exist as Cl2. And if you remember Brinkelhoff from chemistry, that should be your indicator that chlorine is unstable. It wants to be a diatom. So chlorine, as it rises up into the atmosphere and is unstable, is looking to bond to something. And so chlorine will rise as high as the stratosphere, and it will bond to O3 molecules. And what will happen is it will form a ClO with diatomic oxygen. Now, diatomic oxygen and ClO aren't necessarily problems, except for the fact that we've gotten rid of ozone now. So in the presence of chlorine atoms, we see a lack of ozone forming because we see this free radical chlorine bonding to an oxygen. This is called chlorine monoxide. Chlorine monoxide will then interact with free radical oxygen atoms. So the ClO will then react with an independent or free radical oxygen, which we know free radical oxygens are randomly floating around in the atmosphere because UVC light breaks apart diatomic oxygen. And instead we'll get another single chlorine and diatomic oxygen again. That single chlorine now can move around and separate another O3 molecule, and the whole process can start again. A single chlorine atom can jump around to a bunch of O3 molecules and break down up to 100,000 ozone molecules until it finally finds another chlorine atom and we get Cl2. And that chlorine is stable and it will stop depleting O3 molecules. The problem with this is 100,000 ozone molecules is a lot, and this will happen for years and years and years and years. And by years and years and years, I mean 50 to 100 years. So it's a long time that chlorine's residence time in our atmosphere is very high. So what are the effects of ozone depletion? So what happens if we have this hole in the ozone? This may seem obvious, right? Now we have excess amounts of UVA, UVB, and UVC hitting the surface of our planet. Of course, this can cause an excess of skin cancer in people, problems with human eyes like cataracts. It can be harmful for the cells of plants. We know that plants need sunlight to photosynthesis, but actually too much UVB reduces their ability to convert sunlight into usable energy. So we don't want too much UVB. It can also kill phytoplankton. We know phytoplankton are the base of many aquatic food webs, so we could start to see the destruction of an entire aquatic food web based on phytoplankton not being able to survive that increased amount of UVB radiation. And of course, if we are decreasing the ability of plants to photosynthesize with too much UVB, then we can also see the destruction of entire food webs on a terrestrial level as well. Now, one phenomenon that you need to be aware of regarding ozone in the stratosphere, or stratospheric ozone, is something called an Antarctic spring. So this is a natural depletion of ozone in the southern hemisphere. I say natural, it is sort of natural. To this sort of large phenomena of this is considered natural, but the excess chlorine in the atmosphere is sort of anthropogenic. So what happens in an Antarctic winter, now keep in mind, if we're in the Antarctic, we are in the southern hemisphere. Something kind of unique happens. We create something called stratospheric ice clouds. And these ice clouds contain ice crystals. Now, this should immediately sound weird to you just because you should know that most weather, clouds are a part of weather, actually only occur in the troposphere. But during extremely harsh Antarctic winters, we can actually see really cold stratospheric clouds actually sit in the stratosphere. And those stratospheric clouds are actually going to contain a bunch of ice crystals. When these stratospheric clouds are forming, those ice crystals are going to freeze whatever gases are present around them. And a lot of times that might be oxygen, but it might also be chlorine atoms. So at the beginning of the spring, when the temperatures start to warm in the Antarctic, we will start to see those stratospheric clouds begin to melt. And what will happen is all of those frozen crystals that were sitting in those clouds are going to melt as well. And any gases that were contained in those crystals are going to start to release, are going to melt and be released into the atmosphere. So what we see happening is all of this chlorine that was frozen for a really long period of time released all at one time, so very dramatically. So those chlorines are going to then be released into the atmosphere, and you will see a rapid degradation of the ozone. And so the Antarctic spring actually brings a large hole to the ozone in that particular area, or at least very thin. But this is temporary because as the whole season starts again, we'll start to see the chlorine refreeze back up and the ozone hole will go away. Now, this phenomena would be lessened if there was less chlorine sitting in the stratosphere. So if we had less CFCs, or if we were using less CFCs and there was less chlorine sitting in our stratosphere, then this phenomena would have a lesser of an effect. But now keep in mind, we do have some naturally abundant chlorine in our atmosphere. So what do we do to reduce these CFCs since they proved to be such a problem for stratospheric ozone? In 1987, we had something called the Montreal Protocol. This is where 180 nations committed to reduce their CFC production by 50% by the year 2000. The US sort of went above and beyond, really. And by 1994, they had just said no more CFC production here in the United States, no more use of CFCs here in the United States. This was really great. We effectively cut out the use of CFCs, and it worked really, really well. So this should mean awesome, no more problem. We've eliminated CFCs. It didn't work quite as well as like phasing out lead, where we saw almost immediate results. Because lead was so dense, it falls from the atmosphere. We really didn't see atmospheric levels of lead anymore after we phased that out of gasoline. CFCs are incredibly stable, and they stay in the stratosphere for very long periods of time. Like I said, anywhere from 50 to 100 years. So even after we phased CFCs out by 1994, the amount of CFCs in the atmosphere remained relatively stable, at least here in the United States. And also remember, air moves around. So just because we're releasing CFCs right here in like either California or another state doesn't mean they aren't moving as they make their way to the stratosphere. So it will be a while, another 50 to 100 years before we actually see the effects of the Montreal Protocol. Now, not all countries have phased out CFCs entirely, so we do still see some countries using CFCs actively. Now, your next question should be, if we phased out CFCs, what did we replace them with? Well, we replaced them with something called hydrofluorocarbons. And if you look at that term, there is no chlorine atom in there. There's just hydrogen, fluorine, and carbon. And these are better because now the chlorine portion of the CFCs, which was what we were most concerned about, has been eliminated. HFCs work just as well in the same capacity, so we're able to effectively replace all CFCs with HFCs. and eliminate that use of chlorine. The problem, of course, there's always a catch, right? HFCs are an insanely robust greenhouse gas. So they don't actually make their way up to the stratosphere. They sit in the troposphere, and they have an even longer residence time in our atmosphere than CFCs do. And so they contribute largely to the greenhouse effect. Now, if you're not familiar with what the greenhouse effect is or what greenhouse gases are, that's our next section, 9.3 and 9.4. But HFCs are one of the greenhouse gases that we're going to add to our list of gases to be concerned with. Okay, I think that's it. Let me know if you have questions, and I'll see you in class. Thanks.